Why do small changes sometimes cause huge effects, while big efforts can have almost no impact? That's the mystery behind the nonlinear input-output response paradox. In many natural systems, the response is not proportional to the input. A slight rise in nutrients might cause an entire ecosystem to collapse or explode in growth. It's like using a dimmer switch and getting either total darkness or sudden brightness with just a tiny turn. Clearly not what we'd expect from a simple, linear response. So, what's going on inside these systems? They often have thresholds and feedback loops. Once a critical point is passed, everything can change at once. For example, why does a nerve suddenly fire with just a tiny signal? Because it crossed the activation threshold. Or how can a small financial change shake an entire market? Because all parts are connected and sensitive. These nonlinear systems act more like a roller coaster than a straight ramp, unpredictable, fast-changing, and full of surprises.
How do some natural systems exhibit responses that are disproportionately large or small relative to their stimuli, even when one might expect a straightforward proportional relationship based on linear models? In many conventional frameworks, particularly within classical physics and engineering, systems are often modeled as exhibiting a linear relationship between input and output. This means that doubling the stimulus should typically result in a doubling of the response. In a perfectly linear world, every unit of input has an equal, predictable effect on the system's behavior. Yet, a myriad of natural systems, from the firing of neurons and the switching of genetic networks to climate responses and ecosystem dynamics, reveal responses that are unexpectedly amplified or suppressed. This is the essence of the nonlinear input-output response paradox. So far, so good, until we delve more deeply into the intricacies of natural responses. The nonlinear input-output response paradox emerges when the neat proportionality assumed by linear models collides with the inherent complexities of interacting components, threshold behaviors, and feedback loops that abound in natural systems. Under ideal conditions, in a simplified model, one might expect that an increase in stimulus would produce a corresponding increase in response. However, in many real-world phenomena, small increments in stimulus can trigger disproportionately large responses, or conversely, the system may dampen even significant stimuli, resulting in minimal output. One striking example can be found in neural networks. Neurons typically exhibit a threshold behavior. A stimulus must reach a critical intensity to provoke an action potential. Once this threshold is crossed, the neuron fires an all-or-nothing signal, a response that is far larger than the incremental change in the stimulus. This avalanche-like behavior is mirrored in other biological systems, such as hormonal responses or gene regulatory networks, where nonlinear kinetics lead to rapid switches between states. Much like the unpredictable shortcuts in reaction kinetics, or the sudden onset of turbulence in fluid flows, the nonlinear responses in these systems highlight that even minute changes in input conditions can tip the balance, unleashing cascades of activity that defy linear expectations. At even more complex scales, the interplay of feedback loops and network interactions further complicates the picture. In many ecological and climatological models, feedback mechanisms can cause responses to escalate dramatically or be suppressed entirely. For instance, a slight warming may trigger ice melt, which in turn reduces the Earth's albedo, its ability to reflect sunlight, thereby accelerating further warming. A nonlinear feedback loop that produces a response far greater than what the initial temperature change might suggest. Conversely, stabilizing feedbacks can also exist, wherein an amplified input is counteracted by mechanisms that dampen the resultant effect, leading to a surprisingly muted output. And then there is the matter of system sensitivity and hysteresis. In systems with high sensitivity to initial conditions or external perturbations, the prior state of the system, its history, can dramatically influence its response to new stimuli. This history dependence means that two nearly identical inputs can yield radically different outputs depending on the system's current configuration. A behavior that challenges the simplistic linear models where only the immediate stimulus is considered. So what is truly happening? The paradox does not signal any failure in the fundamental laws of physics or biology. Rather, it underlines the limitations of oversimplified linear response models when applied to systems characterized by complex interactions, thresholds, and feedback. The enormous diversity of natural responses is rooted in the fact that many systems operate in a regime where small perturbations can either be exponentially amplified or effectively nullified by the collective dynamics of their component. In other words, while the fundamental rules governing individual interactions may be well understood, their collective manifestation in a high-dimensional interconnected system leads to emergent phenomena that are inherently nonlinear. The nonlinear input-output response paradox serves as a powerful reminder that our intuitive linear interpretations of cause and effect are often insufficient to capture the rich dynamics of natural systems. It challenges researchers and engineers to embrace a more nuanced view, one that accounts for threshold effects, feedback loops, history dependence, and the possibility of multiple stable or metastable states. By developing models that can incorporate these complexities, we gain deeper insights into a wide array of phenomena, ranging from neuronal firing and biological regulation to climate dynamics and beyond. This richer understanding not only advances fundamental science, but also informs the design of more robust technological systems and intervention strategies in complex real-world environments. The nonlinear input-output response paradox reveals that some natural systems respond to stimuli in ways that are not directly proportional to the input, resulting in outputs that are either disproportionately large or small. This behavior contradicts the traditional expectation that a system's response scales linearly with the strength of the stimulus. The paradox highlights that underlying complexities and interactions can amplify or dampen responses unexpectedly. For example, in ecological systems, a small change in nutrient availability can sometimes trigger a massive population boom or collapse. Analogy: it is like a dimmer switch that, instead of gradually changing the light, sometimes causes a room to suddenly flicker into brightness or darkness with only a slight adjustment. Linear response models predict that changes in output will be directly proportional to changes in input, following straightforward, predictable patterns. In contrast, nonlinear systems demonstrate responses that can be erratic, threshold-dependent, or disproportionate relative to the stimulus. This distinction is fundamental to understanding why some systems behave counterintuitively when faced with external perturbations. Example: in a simple resistor circuit, voltage and current maintain a linear relationship, whereas in certain chemical reactions, a minor catalyst change can lead to explosive reaction rates. Analogy: it is like comparing a steady, uniform ramp to a roller coaster, where small shifts in the track can lead to extreme ups and downs. At the microscopic level, nonlinear responses often arise from inherent thresholds and feedback loops within the system's components. When a stimulus surpasses a critical threshold, positive feedback can amplify the response, while negative feedback may suppress it. These mechanisms, operating at small scales, collectively lead to an emergent behavior where the overall response is nonlinear and unpredictable. Example: in nerve cells, a tiny change in voltage can trigger an action potential once a specific threshold is reached, resulting in a large-scale signal. Analogy: it is like a snowball effect where a small push initiates a cascading chain reaction, rapidly escalating the outcome. Nonlinear interactions occur when the influence of one component of a system on another is not simply additive but interdependent, leading to cascading effects. These complex interactions can cause minor changes in one part of the system to propagate and trigger major changes elsewhere. Such dynamics are central to the paradox, as they explain why outputs may be disproportionately sensitive or insensitive to input. Example: in economic markets, a slight shift in interest rates can cascade through the financial system, precipitating large-scale market corrections. Analogy: it is like a network of interconnected dominoes, where tipping one small piece can lead to the collapse of a much larger structure. The interconnected nature of many natural systems means that the response of the entire network is influenced by the complex interplay between its numerous components. Emergent behavior arises when these interactions produce a collective response that is qualitatively different from the responses of individual parts. This network effect is a key reason why nonlinear responses can be highly unpredictable and sometimes vastly disproportionate to the original input. Example: in social networks, a seemingly insignificant rumor can rapidly spread and lead to widespread social phenomena. Analogy: it is like individual instruments in an orchestra that, when played in concert, create symphonies far more dynamic and complex than any solo performance. External stimuli interact with the internal structural complexities of a system, modulating its response in ways that can either amplify or mitigate the effects of the stimulus. The inherent variability and adaptability of a system's internal components often lead to responses that defy simple, straightforward predictions. This interplay is central to understanding why some systems exhibit disproportionately large or small outputs relative to a given input. So, example, in climate systems, small perturbations such as minor changes in solar radiation can trigger significant shifts in weather patterns due to the complex interactions within the atmosphere and ocean. Analogy, it is like a finely tuned musical instrument that, depending on subtle adjustments, can produce unexpectedly rich or muted notes. The nonlinear input-output response paradox has significant implications for the modeling and prediction of system behavior across many fields. Traditional linear models often fail to capture the critical thresholds and feedback loops that drive these complex responses. This underscores the need for sophisticated nonlinear models and simulations to accurately predict and control system behavior in real-world applications. Example, in pharmacology, dosing regimens must account for nonlinear responses in metabolism and drug interaction, as small changes in dosage can result in disproportionate therapeutic effects or side effects. Analogy, it is like attempting to predict the ripple effect in a pond when a single drop is thrown in. A linear approximation falls short of capturing the full dynamic cascade. Capturing the nuances of nonlinear responses in natural systems presents formidable challenges due to the intricate and interdependent nature of their internal processes. Small measurement errors or oversimplifications in a model can lead to large deviations in predicted outcomes. These challenges necessitate the use of advanced computational tools, high-resolution data, and iterative refinement of models to reliably describe and predict nonlinear dynamics. Example, in ecosystem modeling, slight inaccuracies in representing species interactions can lead to vastly different predictions about biodiversity and population dynamics. Analogy, it is like trying to capture the detailed choreography of a complex dance with a low-resolution camera. The subtleties and emergent movements can be easily lost or misinterpreted. Future research in nonlinear system dynamics aims to develop more robust models that integrate multi-scale interactions and adaptive feedback mechanisms. Advances in computational power and data analytics are expected to significantly enhance our ability to predict and manipulate nonlinear responses in a range of natural systems. These insights hold the promise of transformative applications across fields such as climate science, medicine, engineering, and social sciences, where controlling and harnessing nonlinear effects could lead to groundbreaking technologies and strategies. Example, emerging artificial intelligence models are being designed to adaptively learn and predict nonlinear behaviors in complex systems like urban traffic or global weather patterns. Analogy, it is like transitioning from a static two-dimensional map to a dynamic three-dimensional simulation that reveals the hidden complexities and interconnected layers of a bustling, ever-changing city.